In the previous two videos, I talked about the concept of pulse transfer function and how we can analyze different kind of topologies using the concept of pulse transfer function. Now, our goal is to try to analyze a real physical digital control system from the perspective of pulse control transfer function. Okay, so this is a typical fundamental block diagram topology that we want to analyze in this course. Okay, we have reference input. As you can see, this reference input is in a continuous time signal. Okay, it can be discrete in some cases, but let's start with a continuous time case. Okay, and here, as you can see, for analysis purposes, we are sampling the reference signal. Okay, so R star of t. Okay, so y of t is also a continuous time signal. It's the output, and we are also sampling the y of t from the perspective of analysis using the idea of pulse transfer function. But however, as you can see, there's a difference block here. E of t is equal to R of t is minus y of t. And when we sample E of t to obtain E star of t, we also sample R star of t minus Y star of t. So it's not that we are just virtually sampling Y and R. We technically sample both R and Y, their difference, since it's a linear system, at this sampling phase. Okay, good. So let's clean it. I'm sorry for that. Okay, so I couldn't do this. So it's an object tracer. Okay, no problem. So error, which is the input of our purely digital controller. Okay, here. Okay, it produces discrete time outputs, U of k. But we know that we can also model discrete time signals since they are living in digital control system domain using start input signal. Okay, so U star of t or U of k is technically processed with a zero order halt operator, which produces purely continuous time outputs. And we have a continuous time transfer function, which is the plant that we want to control, and it produces the output. Okay, so the goal is computing y of z, R of z, where y of z is Laplace transform of the sampled output, and R of z is the z transform of the sampled input or reference signal. Okay, so and I will derive this using two different approaches. Okay, one of them is more purely discrete point of view. In the other case, we will try to use start signals, start Laplace transform as much as possible. Okay, so let's look at this. So this is a continuous time transfer function. Let's call it gz of zo, let's say s, and this is plant transfer function, and a combination of this is called g of s. Okay, so g of s is equal to y of s divided by u star of s, and it is equal to, we know that, 1 minus e to the power minus ts divided by s times gp of s. Okay, so what we can do is, our goal is computing g star of s, and similarly we want to compute g of z. Okay, so what is g of z? What is g star of s? Let's analyze it using the derivations that we did in the previous lectures. Okay, so as you know, what we do is this. Let's clean that. Okay, g of s is equal to 1 minus e to the power minus ts times gps divided by s. Okay, so if you want to compute g of s, it is equal to g of z, which is equal to 1 minus e to the power minus 1 times z transform of gp of s divided by s. Okay, and later I will solve an example and we will go to this. Okay, so what we did is, now we find a discrete time transfer function which technically maps input signal u of k to sampled output signal. Okay, this is g of z. Okay, so let's look at this. Here we have gc of z. This is a purely discrete time signal. This is g of z. We have y of k. This is e of k. As you can see, it's a purely discrete time signal. Input is discrete, output is discrete. Okay, so if I analyze it, well, I can clearly write like this. Okay, so let's forget that. Okay, it's nice. So E of k is what? Equal to, technically, R of k minus Y of k, right? We know that E of t is equal to R of t minus Y of t. If you sample E of k, you obtain this. So what we can do is, technically, once you discretize your Planck transfer function here, combined with the zero order whole to obtain G of z, we can transform everything in a complete discrete time domain, because this is a discrete time equation, okay? This is a discrete time expression and everything is discrete. So what we can do is we can reduce the system into this form, okay? So once you discretize your plant together with the zero order whole operation, we can technically transform everything in a purely discrete time domain. Okay, and if you compute Y of z divided by R of z, we simply apply the feedback rule, and we can easily see that it is equal to G of z, G of z, 1 plus GC of z times G of z. Okay, this is the pulse transfer function. Okay, so what we did is we discretized the continuous part simultaneously, and then we analyze everything from the purely discrete time perspective. Okay, we just use the start operation to technically discretize this G of S. Okay, so this is the first approach, and I like clean it and make the derivations using the second approach. Okay, and later we will try to solve an example. Okay, this is good. Let's clean everything again. Okay, now let's try to analyze everything from a continuous time perspective and using star operation instead of real sampling. Okay, this is good. So this is still G of S, okay? Okay, this is G of S, there's no problem. Okay, so in this case, what we need to do is first, we have GC of Z. Okay, it is a discrete time transfer function. It's a digital controller. Okay, so we will technically map it to GC of S, which is equal to GC of Z, where we transform Z using the mapping from Z to E domain, e to the power Ts. Even if this is a purely discrete time signal, since Z domain expression is closely related to start S domain expression, we can obtain this star signal. Okay, so what we have is now we can ignore all of the pure discrete time signals and think everything from the perspective of start operation, clean this, and instead of that, we have here G, C, star of S. And let's analyze everything from the perspective of continuous time transfer function and use star operation, try to obtain pulse transfer function. Okay, so in this case, we know that, okay, E of t is equal to R of t minus Y of t. Okay, that's good. There's no problem. So let's try to find transfer function from the R star of t, E star of t first. Okay, so E of t is equal to R of t minus what? Instead of Y of t, what we can use is this. E star, okay, so this is, okay, everything's fine. So let's first transfer everything in Laplace domain. E of S equal to R of S minus Y of S. Okay, so E of S is equal to R of S minus, instead of Y of S, I can use this thing, right? E star of S times G C star of S, G of S is equal to Y of S. This is good, everything is nice. Now let's take the star of both sides like this, star. E star of S is equal to R star of S, okay, minus, this has star, this has star, this doesn't have star. So I can just apply star to the G is equal to E star of S, GC star of S, G of S. Okay, so we can find a transfer function from E star of S to R star of S, which will be equal to 1 over 1 plus GC star of S, G star of S. Okay, that's good. There's no problem. So, but what we want to know is what's the transfer function from R to Y star, of course. But we know that Y, so let's change that, Y star of S is equal to E star of S times GC star of S times G star of S. If I plug it here, I can easily obtain that. Okay, so let's clean it. Y star of S divided by R star of S is technically equal to GC star of S, G star of S divided by 1 plus GC star of S, G star of S. Okay, now everything is in star domain. I can transform it to pure discrete time domain. Y of Z is equal to R of Z is equal to GC of Z, okay, G of Z, 1 plus GC of Z and G of Z. So we obtain the same expression, and this transfer function technically is equivalent to this purely discrete time topology. And we know that G of Z is equal to 1 minus e to power minus 1 Z transform of G plant of S divided by S. Okay. So as you can see, even if the concept can be a little bit complicated, the process is not that hard. We should be careful with the sampling, zero-order holds, and other kind of details. Okay, good. So I want to solve a very simple example to get a better idea of what we can accept in a digital control system. Okay, so this is the topology. Let's go back. Okay, let's clean everything again. Okay, that's good. Okay. Now let's assume that our GP of S, which is a continuous time transfer function, is equal to a simple first order expression such that, okay, GP of S is equal to 1 over S plus 1. That's it. Okay. So GC of Z is given as a simple P or proportional controller, and sampling time is equal to 1 second. Okay, so the only thing that we need to do is first compute G of Z. G of Z is equal to 1 minus Z to power minus 1 times Z transform of G plant S divided by S. Okay, G of Z is equal to 1 minus Z to power minus 1 times Z transform of, okay, 1 over S times S plus 1. Okay, that's good. It's nice. Okay, so what we need to do is we need to do first partial expression. Okay, and it will be like this: Z to the minus 1, Z transform of 1 over S. Okay, not 1. Okay, let's say that. Okay, A over S plus B over S plus 1. You need to compute A and B, and then you need to look at the Z transform and Laplace transform tables, and you will see that G of Z will be equal to 1 minus e to power minus 1 divided by Z minus e to power minus 1. Okay, that's it. Okay, so I'm leaving e to power minus 1, but in the midterm and also mini projects, you can just use numerical values instead of this kind of weird signals. Okay, it's not a big deal. Okay, so we computed G of Z. So what we need to do is let's compute T of Z, which is a transfer function from the sampled input to sampled output. Okay, let's do that. At least understand what we should do and get the basic idea here. Okay, so what is T of Z? T of Z is equal to G of Z, GC of Z, which is a simple P controller, 1 plus G of Z, GC of Z. Okay, T of Z is equal to Kp 1 minus e to power minus 1, Z minus e to power minus 1. Okay, 1 plus Kp 1 minus e to power minus 1, Z minus e to power minus 1. Okay, so if I simplify everything, I will find that this is equal to Kp 1 minus e to power minus 1, Z plus Kp minus K plus 1 e to the power minus 1. Okay, that's it. It's kind of very simple, as you can see that. So let's assume that Kp is equal to 0.1, and then in that case we will find that T of Z, I think, will be equal to what? 0.063. Okay, and this will be equal to what? Z minus 0.3. So I will later solve different examples, and after the midterm, we will analyze this control system from the perspective of stability and transit performance. But for now, the idea is, given a discrete time or digital control system topology, which has sampling, which has zero order hold, computing the pulse transfer function from the sampled input to the sampled output, which look like this for a general K, okay? And for a specific K, you can compute that.